Today we're going to look at section 6.4, inverse functions. Our objective is to be able to find the inverse from a relation, equation, and graph, and to be able to verify the two functions are inverses of each other by showing that f of g of x is equal to x, and g of f of x is also equal to x. So first, how do you find the inverse? Everything we do today revolves around the idea that we're going to switch the x and y. If you remember that when you're dealing with inverses, you're going to be fine for today. We're also going to be using inverse function notation. So if you remember, function notation was just f of x. But today, we're going to deal with the inverse, so that to show that something is an inverse, we're going to put this little -1 up here. And it's the same thing, if you remember, we did when we had inverses with matrices. When we were solving our matrix equation, we had that little -1. So the first one we're going to look at is the inverse of a relation. Now, these are just ordered pairs, and if you remember, an ordered pair is just an x and a y. And that goes for every single ordered pair. So if I want to find the inverse of this relation, all I'm going to do is physically change every x to a y and a y to an x. So 15 comma -2 becomes -2 comma 15. The next one would become 0 comma 3/4. Then -2 comma -1. 3 comma 4. And then my last one would be √3 comma 12. And just by switching the x and y, I've now found the inverse of this relation. But what happens if it's not a relation? What if I give you an equation? Makes it a little bit tougher, but f of x, if you remember, is the same thing as y. Remember, it's our output, where x is our input. So what happens here? Well, if this is where y is, I'm going to now rewrite that as just x. And where I see an x, I'm going to rewrite it as a y. And now I get an x again. Again, I have to change that one to a y. X again, change it to a y, and then add 3. Typically what we would then do is solve for y. Just like our functions, we like to have y equals. Same thing with our inverses. But if a problem is this complicated, obviously I have 3 y's in here, and if you remember, how did we solve for a variable in this case? In last chapter, we either typed into our calculator, did synthetic division, a whole bunch of crazy stuff. If the problem is this big, which it won't be on a test, you don't have to solve for y. The smaller ones you will have to, and I'm going to show you an example of that next. So this is a much simpler one. Okay, this is just the equation of a line, f of x equals 2/3 x plus 6, or y equals 2/3 x plus 6. So the first step you want to do is, if I see a y, I'm going to call it an x. And if I see an x, I'm going to call it a y. But we don't like this form. We like y equals. So after I do that, I'm going to actually do the algebra to simplify it. So the first thing I'm going to do is subtract 6 from both sides, equals 2/3 y. Now, to get this by itself, I'm going to multiply both sides by the reciprocal, which is 3/2. So I'm going to get 3/2 x minus, now remember, if you multiply fractions, this is -18/2 or -9 equals y. But I can't have y here and y here. What was this y? Well, this y was truly the inverse. So I'm going to rewrite this, and remember, it doesn't matter what side I put the y on. This is the same thing as y equals 3/2 x minus 9. So I can move it to this side. But it's not the same y as this. It now represents the inverse of my original function. And that is now equal to 3/2 x minus 9. So what that means is 2/3 x plus 6 and 3/2 x minus 9 are inverse functions of each other. And once we get to the graph, you'll see what that means a little bit more. Again, f of x is the same thing as y. So I have y equals the 5th root of x minus 6. And my goal, again, if I see x is or y, call it x. And if I see an x, call it a y. But now I want to solve for y. So the first step I'm going to have to do is, since I have the 5th root, to get rid of a 5th root, I have to take it to the 5th power. So remember, I have y minus the 5th root of y minus 6, but to get rid of that, I'm going to take it to the 5th power. This is the same thing as if I had a square root, I would square both sides. If I had a cube root, I'd cube both sides. So now I get x to the 5th power is equal to y minus 6. And then to get y by itself, I'm going to add 6 both sides. But remember, this isn't really y, because this original problem was y. this represents the inverse of my original function. So I have x to the fifth plus 6. So if I have the fifth root of x minus 6, its inverse is the x to the fifth plus 6. So let's look at a graph. If I have this line, now I've put in the points that go through integer values just to make it a little bit easier. So I have negative 10, negative 1, negative 6, 0, negative 2, 1, 2, 2, 6, 3, and 10, 4 to make it a little bit easier for you. So anytime you have a graph, the first thing you want to do is just pick certain points. Now for us, a line, remember you only need 2 points to create a line. However, if I had some crazy looking function, I'd want to pick any critical point, anytime it changed direction, anything that was significant. But remember, you want enough points so that way you can reconstruct the inverse. So what am I going to get if I actually try to take the inverse of this graph? Well, I found critical points. I listed them out. You don't have to list them out, but it might make it easier for you. And then I'm going to just do it like we did with the relation. I'm going to switch x and I'm going to switch y. And if I do that, if I take each of these points and I switch the x and I switch the y, I get a new set of ordered pairs. And then I can just take negative 1, negative 10, those ordered pairs, and I graph them. 0, negative 6. Okay. 1, negative 2. 2, 2. 3, 6. And then 4, 10. Now if I notice, I get the same shape. And if you notice also that 2, 2 happen to fall in the same spot, because if x and y are the same values, when I take their inverse, I'm going to get the same value as well. But now what I need to do is I'm going to connect those points. And when I connect them, it should look like a line as well. Now, what we can tell here is if you switch where x and y are, if I put an imaginary line, a diagonal, okay, that goes through the origin, okay, and has a slope of positive 1, this line right here is my y equals x line, okay, has a y-intercept of 0 and a slope of 1. If I notice, if you kind of turn your head sideways, this is the line of symmetry between my two graphs. And what I mean by that is these 2 points are the same distance away from my line. These 2 points are the same distance away from my dotted green line. Same thing with these 2. I can do that all the way across my graph, even the non-integer points. So anytime you're taking an inverse, what you're really doing is reflecting your points over this imaginary y equals x line, and that's what taking the inverse does. In our next example, I've picked out 5 points that have integer values, and the only reason I did that is to make it a lot easier to graph it by hand. I have negative 9, 10, negative 8, 4, negative 5, 0, negative 2, 4, and negative 1, 10 are the ones that I picked out. And just like before, in order to find its inverse, I'm going to take each of those points and switch the x with the y. And if I do that, I now get 10, negative 9, 4, negative 8, 0, negative 5, 4, negative 2, and 10, negative 1. Alright, so if I go through those, now I can actually connect them. So what I'm going to do is connect these points, and I get the same exact shape. But if you notice here, my original problem passed the vertical line test, which means it's a function. But if I look at my inverse, it does not pass the vertical line test. So just because you start with a function doesn't mean its inverse is also a function. Okay? And what you could do is, what doesn't our original function pass? Well, our original function doesn't pass if we were going to do a horizontal line test. If I draw horizontal lines, it's going to hit my graph more than once, which means when I flip it and do the inverse, my inverse is not going to pass the vertical line test, and vice versa. So if you want to know if you've ever asked, is its inverse a function, you could think, does my original function pass the horizontal line test? If it does, then my inverse is a function. If it does not, like this one fails the horizontal line test, I know my inverse will fail the vertical line test. Now for this, it doesn't really matter, but when we usually get to equations, we always want our inverse to be a function. And a lot of times you're going to see some notation, like we will in the next couple examples, to guarantee that our inverse is a function. So how can you verify if you have two equations that they are inverses of each other? Well, the one thing you can do is use our composition of function, which we did in 6.3. If I take f of g of x, what this means is if I take the g function and substitute it into the f function, once I simplify it, I get an x, and the same thing happens when I take the f function and input it into the g function, I get x. Then I've just verified that they're inverses of each other. Now, if at any time I do one of these two compositions and it does not equal x, then I can stop because I automatically know they're not inverses of each other. So let's go through two examples. My first one is I give you an f of x equals 6x minus 7, just the equation of a line. G of x equals 1 6x plus 7 6, another equation of a line. So if I want to verify that they are inverses of each other, I'm going to use red to signify my f of x. I'm going to use blue for the g of x, just to make it a little bit easier to see. So for my first one, I'm going to do f of, and I'm going to input g of x into it. So what I'm going to do is I'm just going to look at my f function. 6 times x minus 7. Well, anywhere I see an x that was normally inside my parentheses, I'm going to input whatever was in the parentheses. So I'm going to input my g of x, which is 1/6 x plus 7 over 6. And now I'm just going to go through and do the algebra. 6 times 1/6 x is x. 6 times 7 over 6 is positive 7. And I have a negative 7, which gives me an x. So that's good so far. If this didn't equal x, I could go back and double check my algebra. If everything was okay and this still did not come out to x, I would just stop and say not an inverse. But since I got an x, now I want to go to the other side. Now I want to try g of my f of x, which means I'm going to take the g function. Anywhere I see an x, I'm just going to put parentheses. And then I'm going to input whatever the f of x function was, the 6x minus 7. Now I'm just going to go through the algebra. 1/6 of 6x is x. 1/6 of negative 7 is negative 7 over 6. Plus the 7 over 6 I already had equals x. Since they both equal x, I have just verified that yes, f of x and g of x are inverses of each other, but we'll just write our inverses. Okay. Now in this example, you're going to see it looks a little bit crazier. Now if you notice these parts, okay, all this is doing is guaranteeing that both of these ends up being functions. You don't have to worry about it too much now. Most of the problems I give you aren't this technical, but a lot of books and worksheets will put this down because they like to be exact, and they want to make sure that the domain of each of our functions is such that we get a function. So for example, when you take the square root of a number, we know we can't take a square root of a negative or else it's imaginary. What guarantees that this is not a negative number? Well, that means x has to be greater than or equal to negative 2. As soon as this becomes less than negative 2, say a negative 3, we get an imaginary answer, which we don't want. Now, if I want to verify that these are functions, both of these end up being functions, we also want to make sure that the domain of one is the range of the other, and the range of the first is the domain of the second. So again, we're going to talk more about this as we get to transformations and graphs, but this is a technical thing that you will see in some problems. So let's actually go through this. Again, my f of x, I take f of g of x. Okay, and that's going to equal whatever the f function is. And wherever I see an x, I'm just going to put parentheses. And then afterwards, I'm going to input whatever the g function is. Minus 2. And now I'm just going to do the algebra. This gives me the square root of x squared minus 2 plus 2 is just x squared. And the square root of x squared is just x, which is good. Now we're going to do the same thing on the other side. I'm going to take g of f of x, okay? And all that's going to be equal to is the g function, but again, wherever I see x, I'm going to just put a parenthesis, and then I'm going to input whatever the f function was, in this case square root of x plus 2. Well, if I take the square root and I square it, I'm just left with whatever's inside, and then minus 2, so here I get x. So again, I've just verified that, yes, f of x and g of x are inverses. And again, that is implying inverses of each other. So I hope you feel a little bit better about finding the inverse of a relation, which is a set of ordered pairs, an equation, and a graph, and to be able to verify that two functions are inverse of each other by showing that f of g of x equals x and g of f of x equals x.